What if the most fundamental forces we observe, the gentle pull of gravity, the crackling energy of electromagnetism, are not separate at all? What if they are merely two faces of a single underlying field? This is the bold claim we will explore. One universal field lies beneath both gravity and light, a field that possesses the intrinsic ability to pull and to push. When this field pulls matter together on a grand cosmic scale, we perceive it as the familiar force of gravity, the invisible hand that orchestrates the dance of planets and stars. Today, our understanding of gravity is dominated by one of the most successful ideas in the history of science, Albert Einstein's general theory of relativity. This theory paints a majestic picture where gravity is not a force in the traditional sense, but a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of the universe around them, much like a heavy bowling ball warps the surface of a trampoline. Other, smaller objects simply follow these curves, creating the orbits we observe. This idea has been confirmed with breathtaking precision, the bending of starlight around the sun and the detection of gravitational waves from colliding black holes. Under this framework, gravity has always been considered an exclusively attractive phenomenon. Mass and energy tell space-time how to curve, and the curvature of space-time tells matter how to move, always toward other matter. There is no room in the standard equations of general relativity for a built-in fundamental repulsion. It pulls galaxies together to form clusters. It pulls stars together from clouds of gas. It pulls you firmly toward the center of the Earth. Let us now entertain the central idea of this essay, that gravity itself has two sides, one that pulls and one that pushes. In this model, the gravitational field is not solely attractive. It is a composite entity, a dynamic interplay, attractive potential, repulsive potential. The net effect in any region depends on the balance between these two opposing tendencies. We can express this in a simple conceptual equation. G total, G attractive, plus G repulsive. G attractive, G repulsive. This simple addition holds the key to a unified perspective. At everyday scales and within galaxies, now we take the most audacious leap in our conceptual journey. If gravity can both pull and push on a cosmic scale, what happens if this duality manifests itself at the microscopic quantum level? The idea proposed here is that the force of electromagnetism is not a fundamental force in its own right, but rather a local, high-frequency manifestation of the same two-sided gravitational field. It is, in essence, a fractal pattern of gravity. A fractal is a complex, self-similar pattern that repeats itself at different scales. The jagged edge of a coastline looks similarly rugged, whether viewed from a satellite or from a few feet away. This is the essence of a fractal. In this view, the same push and pull dynamic that governs the cosmos also operates at the subatomic level, but in a much more intense and rapid fashion. Imagine the smooth, gentle hills and valleys of the large-scale gravitational field. Now picture that superimposed upon this landscape are incredibly tiny spikes, sharp spikes, rapidly vibrating spikes and dips. These localized high-frequency oscillations of the space-time fabric are what we perceive as electromagnetic phenomena. If gravity and electromagnetism arise from the same underlying field, then their respective force-carrying particles, the graviton, the photon, must also be intimately related. In quantum field theory, forces are transmitted by the exchange of particles. For electromagnetism, this particle is the photon, the quantum of light. For gravity, the hypothesized particle is the graviton, a quantum of space-time curvature. In our unified model, the photon and the graviton are not distinct particles, but are instead two different vibrational modes of the same fundamental entity. They are two songs played on a single instrument. The graviton, as it is traditionally conceived, would correspond to a slow, low-frequency, large-amplitude wave in the space-time field. This idea of a modified two-sided gravity does not exist in a vacuum. It resonates with several ongoing efforts in theoretical physics to address the shortcomings of our standard models. The current cosmological model, known as lambda CDM, is incredibly successful but relies on two enormous patches: dark matter, dark energy. It treats dark energy, lambda, as a cosmological constant, a constant energy density inherent to empty space. Our proposal offers a physical origin for this constant, identifying it as the repulsive face of gravity itself, rather than an arbitrary number added to the equations. Many physicists are already exploring ways to modify gravity to explain cosmic acceleration without invoking a separate dark energy. These theories are broadly known as modified gravity models. For instance, Fr. Gravity alters Einstein's core equations by replacing the Ricci scalar r with a more complex function Fr, allowing gravity's strength to change depending on the curvature of spacetime. Another avenue is conformal gravity, which proposes a theory of gravitation that is invariant under local rescalings of the metric. A scientific idea, no matter how elegant or appealing, is only as good as its testable predictions. While this concept of a two-sided fractal gravity is speculative, it leads to several potential observational signatures that could distinguish it from standard models. These tests, though challenging, provide a clear path forward for verification. One of the most direct tests would be to search for subtle connections between extreme gravitational fields and electromagnetic phenomena. Extreme gravitational fields, electromagnetic phenomena. If charge is indeed a form of localized spacetime stress, then in the vicinity of objects with immense gravity and strong magnetic fields, like magnetars, we might observe unique signatures or couplings not predicted by standard theory. Another set of predictions lies in the realm of cosmology. If dark energy is the repulsive side of gravity, its effect might not be perfectly constant over cosmic time and space. Its strength could vary slightly depending on the large-scale distribution of matter and voids. Precision measurements of the expansion history of the universe, using next-generation telescopes like the Vera C. Rubin Observatory, could detect such subtle deviations. The way giant voids in the cosmic web grow over time might also differ slightly from standard predictions, offering another window to test the theory. On a microscopic scale, the idea that a photon is a high-frequency graviton suggests that under extreme conditions, their behaviors might converge. Perhaps in the aftermath of a particle collision at energies far beyond what the Large Hadron Collider can produce, we might find evidence of photons exhibiting minuscule gravitational effects, or vice versa. Furthermore, if electric charge is a geometric feature, it might be possible to design highly sensitive laboratory experiments to detect the minuscule space-time curvature associated with a concentration of charge, a gravitational field produced not by mass but by charge alone. This would be a revolutionary discovery. In conclusion, the proposition that a single two-sided field governs both gravity and electromagnetism offers a profoundly simple and unifying perspective on the universe. It recasts dark energy as an intrinsic part of gravity and redefines electric charge as a geometric stress in space-time. While this remains a bold hypothesis awaiting rigorous mathematical formulation and experimental testing, it invites us to keep an open and curious mind. Great leaps in science often begin with such, what-if questions, challenging us to look for deeper connections and simpler principles. The ultimate verdict will be written in the language of data and observation, a story that the cosmos is waiting to tell us.